In a gray concrete weapons factory in East Berlin, 1953, Soviet-trained engineers gathered around several captured American M1 Garand rifles, ordered by their government to reverse-engineer these legendary weapons that had armed the Americans who defeated Nazi Germany. What followed was 4 years of technical frustration, manufacturing disasters, and ultimately a humiliating admission that East Germany's vaunted socialist industrial system couldn't replicate a rifle design that was already 15 years old. This is the story of communist incompetence meeting American engineering excellence and losing badly.
The divided arsenal. When Germany surrendered in May 1945, the victorious Allies carved the defeated nation into occupation zones. The Soviet Union took control of the eastern portion, which would become the German Democratic Republic, East Germany, in 1949. From the beginning, the Soviet occupation authorities stripped East Germany of industrial equipment, shipping entire factories to the Soviet Union as war reparations. What remained became the foundation for a new communist state that would serve as the Soviet Union's westernmost outpost in the Cold War. By 1950, as Cold War tensions escalated and the Korean War began, the Soviet leadership decided that East Germany needed its own military forces, the Nationale Volksarmee, or National People's Army. But equipping this new army presented immediate challenges. The Soviets were unwilling to provide their newest weapons to their German satellite, distrusting their former enemies despite East Germany's communist government. East Germany would have to produce its own weapons or accept obsolete Soviet hand-me-downs. The East German leadership, eager to demonstrate their regime's legitimacy and technical capability, pushed for domestic weapons production. The State Planning Commission established weapons manufacturing facilities and assigned experienced engineers, many of whom had worked in Nazi Germany's arms industry, to develop or copy weapons for the new army. Colonel Engineer Wilhelm Hartmann, appointed director of the VEB Metal Warren Fabric Weapons Facility in Suhl in 1951, was a survivor who had learned to navigate totalitarian systems. He had worked as a mid-level engineer at Mauser during the Nazi era, avoiding direct involvement with the regime while developing sufficient technical expertise to be valuable. After the war, he convinced Soviet occupation authorities that he had never been a Nazi Party member, a lie, but one that couldn't be easily disproved given the chaos of post-war Germany, and was assigned to weapons development work. "We need to arm the Volksarmee with modern rifles," Hartmann was told by his political commissar, Hans Richter, a communist true believer who had spent the Nazi era in Moscow and returned to East Germany in 1945 with complete faith in Soviet superiority. The Soviet Union has provided examples of American weapons captured in Korea. Your task is to study these weapons and produce superior German socialist versions. Among the weapons provided for examination were 3 M1 Garand rifles, captured from American forces in Korea and shipped to East Germany via Moscow. Hartmann examined the rifles with mixed feelings. As a German engineer, he recognized the Garand as a remarkable weapon, rugged, reliable, and representing a significant advance over the bolt-action rifles that had dominated World War II. But as someone now working in a Soviet-dominated system, he also understood that acknowledging American technical superiority was politically dangerous. The M1 Garand, designed by Canadian-American John Garand and adopted by the U.S. military in 1936, was the first semi-automatic rifle to be standard issue for any military in the world. It fired the powerful .30-06 cartridge held 8 rounds in an N-block clip that fed from the top of the action and operated via a gas system that tapped propellant gases from the barrel to cycle the action automatically. The rifle had proven itself in combat from 1941 through 1945, earning General Patton's famous praise as the greatest battle implement ever devised. "Can we produce this rifle?" Richter asked, his question carrying the weight of political expectation rather than genuine inquiry. Hartman wanted to say no immediately. The Garand was a complex weapon, requiring precision manufacturing, high-quality materials, and sophisticated heat treatment processes. East Germany's industrial base, stripped by Soviet reparations and operating under the inefficiencies of central planning, was struggling to produce even simple consumer goods reliably. Attempting to manufacture a weapon as sophisticated as the Garand seemed foolhardy. But saying no to a direct question from a political commissar was dangerous. Richter represented the Socialist Unity Party and had the power to end Hartman's career, or worse, if he detected insufficient enthusiasm for assigned tasks. "We can attempt it," Hartman said carefully, "but it will require time, resources, and realistic expectations about our capabilities. This is a sophisticated weapon that will test our manufacturing infrastructure. The socialist system can achieve anything the decadent capitalists can achieve," Richter replied, his voice carrying the certainty of ideological faith. "You will have 2 years to produce working prototypes. The Volksarmee needs modern rifles, and you will provide them."
The engineering challenge. Hartman assembled a team of engineers and technicians, drawing on survivors of Germany's wartime arms industry who had ended up in the Soviet zone. Many were skilled and experienced, but all were operating within constraints that made their task nearly impossible. The first step was complete disassembly and documentation of the captured M1 Garands. Chief engineer Klaus Becker, who had worked at Walther during the war, led this effort. "This is beautifully made," he said quietly as they examined the rifle's components. "Look at the machining quality, the precision of the tolerances, the quality of the steel. American industry at its finest." The receiver was machined from a solid steel forging requiring multiple operations on precision machine tools. The barrel was made from high-grade ordnance steel, carefully rifled and heat-treated. The trigger mechanism was complex, with multiple parts requiring precise fitting to function smoothly and reliably. The gas system involved carefully calculated ports and a piston that had to operate within tight tolerances. Every component spoke to manufacturing capabilities that East Germany simply didn't possess in 1953. The country's machine tools were largely worn-out equipment from the Nazi era, inadequately maintained and increasingly unreliable. The steel industry, disrupted by war damage and Soviet reparations, struggled to produce consistent quality metals. Quality control systems were rudimentary, and the central planning system that governed industrial production prioritized quantity over quality. "We need to create detailed technical drawings," Hartman instructed his team. "Every dimension must be measured precisely. Every material must be analyzed to determine composition. We need to understand not just what the rifle looks like, but how it functions and why it's designed the way it is." The measurement process took months. Engineers used micrometers, calipers, and other precision instruments to document every dimension of every component. But they quickly encountered problems. Their measuring equipment, manufactured in East Germany or inherited from pre-war stocks, lacked the precision of American instruments. Measurements varied slightly each time they were taken, making it impossible to determine exact specifications with confidence.
Materials analysis presented even greater challenges. The team needed to determine the exact composition of the steel used in various components. The receiver required different properties than the barrel, which required different properties than springs or other parts. East Germany possessed basic metallurgical analysis equipment, but it was primitive compared to American standards. They could identify major alloying elements, but struggled with trace elements and couldn't definitively determine heat treatment processes. The steel in the receiver appears to be a medium carbon alloy steel with nickel and chromium, reported the metallurgist Ernst Fischer. But I cannot determine exact percentages of the alloying elements, and the heat treatment process is unclear. We can see the microstructure under microscope and know it's been hardened and tempered, but we don't know the temperatures or timing used. The gas system proved particularly problematic. The M1 Garand used a relatively simple gas system with a piston that drove an operating rod, which in turn unlocked and cycled the bolt. But the system's reliability depended on precise dimensions of the gas port, gas cylinder, and piston. Variations of even a few hundredths of a millimeter could cause malfunctions. Too little gas and the action wouldn't cycle. Too much, and parts would be subjected to excessive stress and accelerated wear. We need to not just copy the dimensions, but understand the relationships between components. The gas port size, the weight of the operating rod, the strength of the operating spring, all these interact to make the system function reliably. If we change one without understanding how it affects the others, we'll create a rifle that doesn't work. By late 1954, after more than a year of study, Hartmann's team had created a complete set of technical drawings and specifications for a weapon they designated the Selbstlader M53, Self-Loading Rifle Model 53. The drawings represented their best attempt to replicate the M1 Garand using available materials and manufacturing processes. But Hartmann knew they had made numerous compromises in substitutions that would likely affect performance. The receiver would be manufactured from East German steel that was similar, but not identical, with the American original. The barrel would lack chrome lining because East Germany didn't have barrel chroming capability. Various small components would be made from materials that approximated American specifications, but they weren't exact matches. And the manufacturing tolerances would be looser than the M1 Garand specifications because East German machine tools couldn't consistently hold tighter tolerances. This rifle will look like an M1 Garand, Hartmann told his deputy privately, but it won't perform like one. We've made too many compromises. I give it even odds whether the prototype will even function.
Manufacturing nightmares. Production of the first prototypes began in early 1955 at the Suhl facility, which had been equipped with machine tools gathered from various sources. Pre-war German equipment, some Czech machines acquired through trade, and a few Soviet tools of dubious quality. The workforce consisted of experienced machinists who had worked in Germany's wartime arms industry, mixed with younger workers trained entirely in the East German system. Problems emerged immediately. The receiver forgings produced at a state-owned steel mill showed quality variations from piece to piece. Some were harder than specified, making them difficult to machine and prone to breaking cutting tools. Others were softer than required, meaning the finished receivers might not have adequate strength. Attempts to reject substandard forgings were overridden by plant managers under pressure to meet production quotas. Quantity mattered more than quality in the central planning system. "We cannot work with these forgings," the shop foreman complained to Hartmann. "Half are out of specification. If we try to machine them, we break tools and waste time. If we use them anyway, the receivers may fail during proof testing or in service." "Do your best," Hartmann replied, knowing his answer was inadequate but having no authority to force the steel mill to improve quality. Machine the forgings carefully. Reject only the worst ones and document everything. When problems occur, at least we'll have records showing we identified issues. The machining process revealed the limitations of East German equipment. Machine tools that had been adequate for producing World War II-era bolt-action rifles struggled with the tighter tolerances required for a semi-automatic rifle. Tools wore out rapidly. Dimensions drifted as machines heated up during operation, and operators, inadequately trained and working with poorly maintained equipment, made frequent errors. Barrel production was particularly problematic. The rifling process, which cut spiral grooves inside the barrel to spin the bullet for accuracy, required specialized equipment and skilled operators. East Germany had inherited some rifling machines from pre-war factories, but the equipment was worn and outdated. The barrels that emerged showed inconsistent rifling depth and spacing, which would affect both accuracy and reliability. Heat treatment, the process of heating and cooling metal to achieve desired properties, was another failure point. The process required precise temperature control and timing, but the furnaces available at the Sewell facility were primitive, with inconsistent temperatures and no sophisticated control systems. Parts that should have been uniformly hardened emerged with soft spots or, conversely, were over-hardened and became brittle. By mid-1955, the facility had produced components for 10 prototype rifles. Assembly revealed that many parts didn't fit together properly due to dimensional variations. Technicians had to hand-fit components, filing and adjusting parts to make them work together, a time-consuming process that defeated the purpose of mass production and meant that parts weren't interchangeable between rifles. "These aren't production rifles," Becker observed, as technicians struggled to assemble the 6th prototype. "They're hand-built prototypes, each one unique. We can't manufacture rifles this way at scale. We need better materials, better equipment, better processes. We need what we don't have and can't get." The first firing test took place in October 1955 at a military range outside Sewell. Hartman watched nervously as a test shooter loaded an 8-round clip into the first prototype and chambered a round. The rifle fired once, ejected the empty case, but failed to chamber the next round. The bolt had not traveled fully forward, leaving a round partially fed from the clip. The shooter attempted to cycle the action manually, but the mechanism was jammed. Examination revealed that the gas system wasn't functioning properly. Either the gas port was too small, or the piston-to-cylinder clearances were too tight, or both. Insufficient gas pressure was reaching the operating rod to cycle the action reliably. The problem could potentially be fixed by enlarging the gas port, but that required careful calculations and testing, trial and error that would consume time they didn't have. The second prototype fired 3 rounds before the operating rod broke, shearing off at a stress point near the gas piston. Metallurgical analysis revealed that the rod had been improperly heat-treated, creating internal stresses that led to failure. The third prototype fired an entire 8-round clip successfully, raising hopes briefly, but when loaded with a second clip, it fired once and then experienced a catastrophic failure. The receiver cracked longitudinally, splitting open along the right side. Of the 10 prototypes tested that day, only 2 functioned adequately enough to fire multiple clips without major failures, and even those 2 showed problems, extraction failures, feeding malfunctions, and parts that showed excessive wear after limited firing. The prototypes averaged perhaps 200 rounds before experiencing failures that rendered them inoperable. The M1 Garand, by contrast, was designed for a service life of 10,000 rounds or more with proper maintenance. The East German copies were failing at 2% of expected service life, demonstrating just how far their manufacturing capabilities fell short of American standards.
Political pressure and scapegoats. The test failures created an immediate political crisis. The Volksarmee needed rifles. The party had promised domestically produced weapons, and Hartmann's facility had consumed resources for 4 years with nothing to show for it. Political Commissar Richter, who had assured his superiors that the project would succeed through socialist determination, now faced explaining the failures to authorities who didn't accept technical limitations as valid excuses. "These failures are the result of sabotage," Richter declared during a special investigation convened after the disastrous test firing. "Reactionary elements within the engineering staff have deliberately created flawed designs to embarrass the German Democratic Republic and prove their loyalty to Western imperialism." Hartmann recognized the familiar pattern: technical failure reframed as political betrayal, scapegoats needed to protect those who had demanded impossible achievements. "The failures are technical, not political," he argued carefully. "We lack adequate materials, equipment, and manufacturing capabilities. The M1 Garand is a sophisticated weapon that requires industrial infrastructure we don't possess." "Given more time and resources, defeatism," Richter interrupted. "You speak like a saboteur seeking to undermine faith in socialist capabilities. The Soviet Union has achieved remarkable technical feats. The German Democratic Republic can do the same if engineers approach their work with proper revolutionary consciousness rather than bourgeois skepticism." Several engineers were arrested within days, accused of sabotage and espionage. Becker, whose technical knowledge made him particularly valuable, was detained but released after intensive interrogation when investigators couldn't produce actual sabotage. Others were less fortunate. 2 junior engineers were convicted in show trials and sentenced to lengthy prison terms for economic crimes against the socialist state. Hartmann survived the purge largely because his technical expertise was irreplaceable and because he had cultivated relationships with party officials who valued his practical skills over ideological purity. But his position was precarious. The Selbstlader M53 project was officially suspended, and resources were redirected to simpler objectives: licensed production of Soviet weapons designs, which required less independent engineering but at least produced functional weapons.
The SKS solution. By 1956, East German authorities had effectively abandoned attempts to copy the M1 Garand and instead negotiated with the Soviet Union to produce the SKS rifle, a Soviet semi-automatic design that was simpler than the Garand and for which the Soviets would provide complete technical documentation, tools, and even advisors to oversee production. The contrast was instructive. The SKS, while less sophisticated than the M1 Garand, was designed with ease of manufacture in mind. It used stamped and welded components where the Garand used expensive machined forgings. It had looser tolerances that were more forgiving of manufacturing variations. It was designed to function reliably even when made from lower quality materials and with less precise manufacturing processes. In short, it was a weapon suited to Soviet industrial capabilities which were themselves limited compared to American standards. East Germany successfully produced SKS rifles in quantity beginning in 1957, arming the Volksarmy with adequate, if not exceptional, weapons. The rifles worked reliably, were reasonably accurate, and could be manufactured at acceptable cost. They weren't as refined as the M1 Garand, but they were functional, something the Selbstlader M53 had never achieved. "We should have done this from the beginning," Hartmann told his wife privately one evening in 1958, speaking in the quiet privacy of their apartment where listening devices were unlikely but never impossible. "Copying Soviet designs we could manage. Trying to replicate American weapons we couldn't even understand was folly, but no one wanted to hear that. How many resources did we waste? How many careers were destroyed? For what? To prove we could match American capabilities we clearly didn't possess?" The few Selbstlader M53 prototypes that had been produced were stored in a secure facility classified as state secrets to prevent knowledge of the failure from spreading. They remained there for decades, gathering dust, silent testimony to a project that had consumed resources and destroyed careers while producing nothing of value.
The broader pattern of failure, East Germany's failed attempt to copy the M1 Garand, was part of a larger pattern of communist states attempting to replicate Western technology through reverse engineering, while lacking the industrial infrastructure and technical knowledge to succeed. The Soviet Union itself had struggled with similar problems, successfully copying some American designs. The B-29 bomber became the Tu-4, for example, but only by deploying massive resources and accepting production costs far exceeding what would have been required to develop indigenous designs suited to Soviet capabilities. Smaller communist states like East Germany had even less success. They lacked the resources of the Soviet Union, operated under systems where political considerations trumped technical realities, and were trapped in ideological frameworks that prevented honest assessment of their own limitations. Engineers who reported that tasks were impossible faced accusations of defeatism or sabotage. Failures were blamed on individuals rather than systemic problems, ensuring that the same mistakes would be repeated. The M1 Garand represented American industrial and engineering excellence developed over decades. The rifle's development had begun in the 1920s, with John Garand working at Springfield Armory, refining designs through countless iterations and extensive testing. The final design, adopted in 1936, represented the culmination of years of research and development, supported by an industrial infrastructure capable of precision manufacturing and producing high-quality materials consistently. East Germany in 1953 had none of these advantages. Its engineers were skilled, but working with inadequate tools and materials. Its industry was disrupted by war damage and Soviet reparations. Its political system punished honest technical assessment while demanding impossible achievements. Attempting to copy the M1 Garand under these conditions was doomed from the start, but the political system made acknowledging this reality dangerous. Other communist states had similar experiences. China's attempts to copy Soviet designs often produced weapons that looked correct but functioned poorly due to manufacturing quality issues. North Korea's efforts to produce modern weapons resulted in unsafe, unreliable equipment. Throughout the communist bloc, the pattern repeated. Ambitious reverse engineering projects driven by political demands rather than technical reality, inadequate resources concealed by propaganda, and failures blamed on sabotage rather than systemic limitations.
The cost of incompetence. The failed Selbstlader M53 project consumed significant resources that East Germany could ill afford to waste. The engineering team, the manufacturing facilities, the materials and equipment, all could have been directed toward more achievable objectives. Instead, 4 years of effort produced nothing but a handful of non-functional prototypes and ruined careers. The human cost extended beyond the engineers imprisoned or career destroyed by the project's failure. East German soldiers would spend decades armed with weapons inferior to those of their potential enemies, precisely because their government's ideological rigidity and technical incompetence prevented honest assessment of capabilities. Resources wasted on impossible projects meant less available for legitimate defense needs or, indeed, for civilian consumption in an economy that perpetually struggled to meet basic needs. The contrast with West Germany was stark and increasingly painful for East German authorities. West Germany, allied with the United States and integrated into Western economic systems, licensed production of American and Belgian weapons designs. West German factories produced the G3 rifle, a Spanish design based on German wartime research using sophisticated manufacturing equipment and processes.
The weapons were reliable, accurate, and competitive with the best military rifles in the world. East Germany, trapped in the communist bloc and dependent on Soviet goodwill, could only produce what Soviet authorities permitted, generally obsolescent designs using inferior manufacturing processes. The gap between East and West German technical capabilities widened over time, becoming a constant source of embarrassment for a regime that claimed superiority over fascist West Germany.
The final accounting. By the time East Germany collapsed in 1989-1990, the failed Selbstlader M53 project had been largely forgotten even within the country. The prototypes had been destroyed or lost during decades of bureaucratic reorganization. Engineers who had worked on the project were dead or retired. Documents had been misfiled, destroyed, or remained classified in archives that would only gradually become accessible to researchers. Wilhelm Hartmann, the project director, survived the communist era and lived to see German reunification. In his 80s, he gave a few interviews to military historians researching East German weapons programs. "We knew from the beginning it was impossible," he said in one interview conducted in 1992. "The M1 Garand was beyond our capabilities to copy. But you couldn't say that in the German Democratic Republic. You had to appear optimistic, had to claim that socialist determination could overcome any obstacle. Technical truth was less important than political orthodoxy. So we wasted years and resources attempting the impossible. And when we failed, people's lives were destroyed to avoid admitting that the system itself was inadequate." The broader lessons of the failed project remain relevant. Modern weapons are products of entire industrial ecosystems, not just individual factories or engineering teams. Successfully replicating such weapons requires not just copying visible features, but understanding and replicating the underlying capabilities: metallurgy, precision manufacturing, quality control, testing procedures, and accumulated technical knowledge. This can't be achieved through reverse engineering alone, especially in political systems where honesty about limitations is dangerous. East Germany's attempt to copy the M1 Garand failed not because German engineers lacked capability. The same technical talent in West Germany successfully produced world-class weapons, but because the communist system they operated within made success impossible. Inadequate resources, poor quality materials, obsolete equipment, and a political environment where truth-telling was dangerous combined to ensure that ambitious technical projects would fail, regardless of individual effort. The M1 Garand itself continued in service with various militaries for decades after East Germany's failed copying attempt. The rifle proved its worth in conflicts from World War II through Korea and beyond, eventually being replaced by more modern designs, but never forgotten as one of the landmark weapons of the 20th century. It represented American engineering excellence and industrial capability, characteristics that East Germany could observe and envy, but never successfully replicate within its dysfunctional communist system. Today, a few photographs and technical documents in German archives are all that remain of the Selbstlader M53 project. The prototypes are gone, the engineers mostly forgotten, and East Germany itself has disappeared into history. But the story remains instructive as a cautionary tale about the costs of ideological rigidity, the dangers of political systems that punish honesty, and the fundamental truth that technical excellence cannot be achieved through propaganda and wishful thinking, only through patient investment in capabilities, honest assessment of limitations, and systems that allow technical professionals to work effectively toward achievable goals.
And that's the end of this story. Don't forget to like, subscribe, turn on the notification bell, and share the video to catch our latest historical stories